Okay, so in order to talk about habitability, then obviously an important aspect of that is whether a celestial body, a planet, or a large moon has an atmosphere and has a climate which is suitable for liquid water, usually we think of on the surface of a planet. So I'm going to do 4 lectures, and this first one is fundamentals. And then the second one is going to be origins of atmospheres. So where do atmospheres come from? And why do some planets or some large bodies not have atmospheres at all, whereas some other ones do? So for example, consider Saturn's moon Titan, which has a thick atmosphere with a surface pressure is 1.5 bar, so 1.5 times the Earth's surface pressure. Another body is Ganymede, the largest moon of Jupiter, which has virtually no atmosphere. So it's not just the question of a body's size. There are other aspects to the issue of origins. And then the third lecture is going to be about climate evolution. So the Earth's atmosphere has changed through time, and also that on, for example, Mars, and also on Venus. So why is it that when we look at the 3 terrestrial planets, the Earth is the way it is, Mars is barren, and Venus is barren in a different way to Mars? This is the issue of climate evolution. And I'm going to concentrate on the rocky planets, because I think they're the kind of things that we think of for the exoplanet systems, right? That we want to find Earth-like planets made of rock, primarily. And we want to find one that is not just habitable, but eventually inhabited with life on it. So the next one, the final lecture, will be finding a living planet. The problem is, though, that in order to discuss this subject, I need to introduce some fundamentals, because my experience is that astronomers traditionally have, they may have a course in their first year on the solar system, and that's it. Then it's galaxies and stars. Atmospheres, stellar atmospheres, not planetary atmospheres necessarily. And so even astronomers may not be totally familiar with planetary atmospheres, unless they're a specialist. And yet this is an important topic. And basically, I'm going to start out talking about atmospheric science, but by the 4th lecture, I'm going to undergo modification and evolution and end up as an astrobiologist. Hopefully there's no dissent there. This first lecture is going to be about fundamentals. And so, if we're going to talk about atmospheres, how do we classify them? We had a lecture earlier about classifying biology. But what about atmospheres? What are the different kinds of atmospheres? And then when we look at atmospheres, they have a certain structure to them and a certain terminology. And a lot of atmospheres in the solar system, if you go up, they become colder with altitude. But then you can turn around in temperature and have what's called an inversion, where it gets warmer with altitude, such as in the Earth's stratosphere. And in the Earth's stratosphere, of course, there's an ozone layer which is absorbing the ultraviolet light and causing this increase in temperature with altitude. And finally, the important issue from here to the next bullet is climate. So if you have an atmosphere with these certain properties, the composition, certain structure, how does that relate to the issue of climate? Because climate, it determines habitability. And we care for astrobiology because at least life as we know it requires liquid water. So if we want a habitable planet, we want the surface temperature to be within the range where liquid water can exist. We also care about the composition of an atmosphere because life dumps waste gases into the air. Now sometimes this is useful. If a plant dumps oxygen into the air, other life can use it. But that's not the only gas. There's also methane and there's some trace gases. On the other hand, there's also geophysical aspects of planets that put gases into the air or recycle gases. But at least for the biological gases or biogenic gases such as methane or oxygen, then potentially when we look at exoplanets, there's the potential to detect life indirectly. We can look for the spectral signatures of these gases, and if it's the right mixture, if it seems unusual, if it seems something that couldn't be created abiotically, maybe it means that someone is home on that planet. On the other hand, nature doesn't like free lunch, a free lunch which nobody is eating, okay? If you leave some pizza in the hallway here at in the university area and no one eats it, it means there's no students around, okay? The place is dead, okay? But if it gets eaten or if it disappears, you know that, okay, somebody ate this lunch. It's a free lunch. And so there are some gases that microbes eat. We don't eat them ourselves, but hydrogen, for example, it would be difficult to have an atmosphere with a lot of hydrogen and water on the surface and life there because it would tend to be eaten. And even something that kills us, carbon monoxide, there are microbes that are quite happy to eat that. They just need water and they'll eat and a few nutrients and they'll eat carbon monoxide. So if we found a lot of these gases on a habitable planet, we might say, well, that's an anti-biosignature. No one's home. There's a free lunch. There's a pizza with not being eaten. So all of these parts of atmospheres interact together. There's composition, pie chart. There's radiation, which can also include clouds. There's some chemistry related to the composition. And there are fine particles suspended in the atmosphere, which we call aerosols. And life can modify the composition. It can also, therefore, modify the climate system. And this will happens on the Earth and could happen on other planets. But let me start then with, to borrow a word from biology, the taxonomy, the naming or the classification system of composition. And then from there, I'll talk about the climate system. So if you look in some textbooks on this subject, they might say, well, we have bodies like the Earth, which has a lot of nitrogen in its atmosphere, and so does Titan. And they might also say there's bodies like Mars, which are mostly 96% carbon dioxide. Venus is also about 96% carbon dioxide. And so we could classify them according to the dominant gas. But we sometimes use this word stamp collecting, that it's just arbitrarily classifying things. And in fact, there's a more sensible classification, which is chemical. So in fact, there are two kinds of atmosphere. And one of them is chemically reducing. Now what that means for practical purposes is one that is hydrogen rich in some way. It may be hydrogen gas itself, or it could be a hydrogen-bearing gas like methane, or H2S, hydrogen sulfide, or ammonia. And the kind of atmospheres that we see in the solar system are Titan. So Titan has, in its lower atmosphere, 95% nitrogen and about 5% methane. Okay? And that 5% methane, hydrogen-rich gas, makes it a reducing atmosphere. And what this means is that this kind of atmosphere tells you the chemical character and the kind of compounds that can form in this atmosphere. The giant planets, they're all very hydrogen-rich. They're all reducing atmospheres. The Earth, at one time, not now, but back in the past. So this symbol here, giga-anna, 10 to the 9 years ago, a billion years. So before 2.4 billion years ago, there was very little oxygen in the Earth's atmosphere. And gases such as methane would have built up to higher levels, and it was a reducing, albeit a weakly reducing, atmosphere. Mars today is not a reducing atmosphere, but probably at some point on the very earliest part of history, perhaps before 4.3 billion years ago, Mars may have had a reducing atmosphere. The oxidizing atmospheres that are not hydrogen-rich, so today on the Earth, 21% oxygen, the rest nitrogen, a little bit of argon, very little hydrogen, 0.5 parts per million, very little methane, 1.8 parts per million. The Earth today is oxidizing. Hydrogen poor, oxygen rich. And Venus and Mars, they're mainly carbon dioxide, and they're not reducing. So this indicates chemical character. It indicates whether, say, carbon is in the form of carbon dioxide, such as on Venus, Mars, and the Earth, predominantly, or the reducing form, which is methane. In all of these bodies, Titan, 5% methane, methane, which gives the color to Uranus and Neptune because it absorbs in the red, and then also on early Earth, and perhaps on the very, very early Mars. It also allows us to make predictions about the fine particles. So if we look in the atmosphere of Titan, then there are certain kinds of aerosols, the fine particles, and also on the giant planets, also on the early Earth. But there are different kind of particles in these oxidizing atmospheres, which I'll come to in a second. Now, there are some atmospheres that are not on here. And there are some bodies in our solar system, some of the things that, some of the small bodies that Jack mentioned. So what I'm talking about when I mention these ones are fairly thick atmospheres. Mars is the thinnest on this list here. But there are a whole bunch of thin atmospheres. So when you look at Triton, this is the surface pressure in bar. So it's 1 bar on the Earth. This is microbars. And also on Pluto, microbars. These are just the vapor pressure of the nitrogen that sits on top of an icy surface of ice, nitrogen ice. And then the moons have tiny surface pressures. These are oxygen, which is produced from water on the surfaces of these moons, but these are actually have been detected. So we call these exospheres. Exospheres, that just means the atmosphere is so thin that there's virtually no collisions. That's the definition, broadly speaking, of an exosphere. And these have this oxygen because there are charged particles. They're associated with the envelopes around these Jupiter and Saturn, magnetic fields, envelopes of ions. The ions bash in, hit these moons. They can break up water. The hydrogen escapes easily, the oxygen less easily, and so they have oxygen atmospheres. And then Jack mentioned Io, which is Jupiter's stress ball, squeezing it, and it gives out volcanic gas, mainly sulfur dioxide. And again, this is an extremely thin atmosphere, the surface pressure, 10 to the minus 9 bar. And Enceladus also has a water vapor, very thin atmosphere. It's an exosphere, essentially collisionless. So what happens is that you can now say that these atmospheres, the reducing ones, you can make generalizations about the kind of particles that you have in these atmospheres. If it's hydrogen rich, you'll have methane. The methane can be broken up by ultraviolet light that's absorbed. We call that photolysis, when a molecule breaks with the absorption of light. And the fragments of the methane can join together and they can make bigger molecules, bigger hydrocarbons. This is polyaromatic hydrocarbons, something with more than at least 2 or more benzene rings. And what happens on Titan, you form these particles, they make that haze that Jack showed, his picture of Titan, just this orange-brown planet, in the moon in the visible. And they sediment out to the surface. So in the tropics on Titan, there are lots of dunes, and we think those dunes, they're not made of sand like the sand on Copacabana Beach. They're made of sand-sized particles that are organic particles, sort of soot, if you like, that fall out, they've been made in the atmosphere and have fallen to the surface over time. This happens because the hydrogen can escape from a small body like Titan. On the giant planets, this hydrogen can't escape. There's no arrow here. It's stuck on the giant planets, but you can still have photolysis of these hydrogen-bearing gases. You can make hydrocarbons, particles, just like on Titan. You can make, from phosphine, you can make phosphorus, which is very colorful and may account for some of the colors that we see on Jupiter. You can make hydrazine, you can make sulfur solids, of course, various solids of sulfur. But these things get recycled. They go down to the hot depths below. There's still hydrogen, it hasn't escaped. There's plenty of hydrogen. And at the hot temperatures and pressures, you can reform these gases, and there's a big cycle. Break these up, make particles, go back to gas. This is unlike a small body where the particles go to the surface. So those are the kind of aerosols we get in reducing atmospheres. What about oxidizing atmospheres? What kind of aerosols do we get on the Earth? Or on perhaps Venus is an easier one to think about. Well, these bodies can have sulfur in these atmospheres, and they have different fates, whether the world is dry or wet or cold or hot. This is a picture of the Earth's atmosphere. The sun is setting, and there's a bright layer here where the sunlight is scattering. And this is, in fact, something called the younger layer. It's about 20 to 25 kilometers, and it's a haze of sulfuric acid. Because in an oxidizing atmosphere, the sulfur gases can be oxidized, and they can turn into a particle. It's a very thin layer, so you can only see it in this kind of orientation. But nonetheless, if you have big volcanoes going off on the Earth, they can put these particles into the stratosphere, and it can change the amount of sunlight that gets reflected. And so when Pinatubo, which was a volcano in the Philippines, when it erupted in 1991, if you look at the global warming trend, there's a dip. Pinatubo erupts in 1991. In 1992, there's a bit of a cooling of the Earth because of these aerosols in the upper atmosphere. Venus is much more extreme. So we have this chemical haze around the Earth, but it's very thin. On Venus, it has a photochemical haze around the entire planet that's very thick. So that's why when you look at Venus, you can't see the surface, because this haze is extremely thick. and is reflecting the sunlight directly back at you. So it's so thick that we think of it as clouds, the clouds of sulfuric acid around Venus. And sulfur dioxide is also present, so some of it, when these particles fall down, they get converted back into sulfur dioxide. On the Earth, if these things fall down, they go into the ocean. And so they're gone. But on Venus, the sulfur is stuck in the air because it's so hot. The surface is 460 degrees Celsius approximately. There have been computer models of Mars, and it shows that if you put volcanic gases into the Martian atmosphere, such as sulfur, you would also form sulfuric acid. So you get a haze of particles on Mars as well. And actually, that can actually cool Mars, which is a problem because we'd like to explain why early Mars has signs of liquid water that cut valleys in its surface. If you look at the surface of Mars and you look in the soil, there's 6 to 8 weight% sulfate. That's a lot because the concentration of salt in the ocean out here is only 2.5 weight%. So the soil on Mars has a lot more salt in it, more salt by weight even than seawater, terrestrial seawater. But that's something you expect because the sulfur, once upon a time, was going into the atmosphere of Mars. And where could it go? It can only go into the soil surface. There is no ocean today. It's dry. So the sulfur is accumulated as salts on the surface of Mars. But once it must have gone through the atmosphere. If we dried up the Earth's oceans, we would have a lot of salt in our soil because it's mostly in the ocean. I also want to talk about how we, just introduce briefly, how we talk about composition. So for the Earth, we talk about a mole fraction or a partial pressure or a number density. And this is a mixing ratio, which is simply number of moles of some gas divided by 1 mole of air. So nitrogen, 0.78 mixing ratio, or 78%. And this is the same by the gas laws as partial pressures, or volume fraction, or number density fraction. So we say this is 78% by volume, because that's also the volume fraction, but it's also the partial pressure fraction, and so on. This is for the Earth. And for most atmospheres, we can use the ideal gas law, which is P equals nKT, Boltzmann's constant, number density. And we can replace, by playing around, we can replace things with a density and a specific gas constant, which is just the universal gas constant divided by the molar mass. So that would be 8.314 universal gas constant. On Mars, this would be 44 grams per mole, and you'll get this for this here. So that's some basics of planetary atmospheres. There are 2 types, reducing and oxidizing. It allows you to infer the kind of aerosols you would expect, at least for the solar system that we understand fairly well. And we talk about the compositions in this way. Okay. The next part, structure of atmospheres. Let's take the Earth as a good example, because we know the Earth. So, surface temperature, 290 Kelvin. Mean global average, maybe a bit less than that, 288 or something, which is 15 degrees Celsius. We cool as we go up in the troposphere, and then we turn around to the stratosphere. There's a maximum temperature at the top of the stratosphere, and then a cooling in the mesosphere, and then it warms up a lot in the thermosphere. And these terms were thought of for the Earth. So the troposphere and the stratosphere, that was discovered in the 20th century by a Frenchman called Tesserand de Boer. And he flew kites, and he stopped flying kites because they got caught up in telegraph wires, and that annoyed a lot of people because they couldn't communicate. So he then tried balloons, which were a bit better. And he discovered that it got colder as you go up. People knew that because if you climb a mountain. But then the temperature sort of became steady. And he named the lowest layer the troposphere and the next layer up the stratosphere. He didn't know why this happened. That was discovered later, but all in the early part of the 20th century. And you'll notice here also we've got weather balloons that go up into the stratosphere. You can go up on a balloon, you could jump off. There was a crazy Swiss guy did that recently, right? Felix Baumgartner jumped from, what was that, 30-something thousand feet. And up here in the thermosphere, this is part of the atmosphere, but actually some spacecraft are this low, so they fly through the thermosphere, like the space shuttle, for example. And where the atmosphere joins space is the exosphere. So this is the place where there are essentially no collisions up here. And up to about 100 kilometers, the atmosphere is well mixed. The bulk composition is about the same. But then this is dominated by turbulence. This is dominated above here by diffusion. And then the lighter gases become more abundant. So by the time you get to 2,500 kilometers, the Earth's atmosphere is mostly hydrogen atoms. And these are the distances. It varies between the poles and the tropics, but the stratosphere is about 10 kilometers deep. And the stratosphere goes up to about 50, 55 kilometers, and so on. So you could ask a question, which is, why does it do this? Whoops, wrong way. Why does it get colder as you go up a mountain? So for example, yesterday I went from Copacabana up to Pico da Tijuca. It's about 1 kilometer, and it was definitely cooler up here. But why is that?
Less reflection from the Earth. You have, on the peak, you have less surface of reflection of the heat of the Earth. And then you have less heat, less.
It's not quite the right answer. So it is true that the sunlight comes through, it heats the surface of the Earth.
Yeah.
Okay. But then what happens to the air? What does it do? The Greek tropos means turning. Means turning, which is convection. So the surface is heated by visible sunlight, and it sets up convection. And because of convection, into a region of lower pressure, as an air parcel here, as it goes up, will expand because it's lower pressure, and it will cool as it expands. And the process of convection, also parcels that come down, they will compress and warm, is that eventually in equilibrium it sets up a gradient of temperature set by convection properties, where it's hot here and cooler on the way up. And this temperature here, if this is 25 degrees Celsius, what would be the temperature at the pico?
Yeah.
Sorry? It's not, well, no, that's too much. 15 is too cold. It wasn't that cold. What? 20? Yeah, 20 is about right. What you were saying was the dry lapse rate. So this change in temperature per kilometer is the lapse, called the lapse rate. Okay? And the average for the Earth is 6 Kelvin, the Earth's atmosphere per kilometer, cooling. If it were dry, the dry lapse rate is given by a simple equation, which is the gravity divided by the specific heat capacity of the air, which for the Earth is about 10. And that's about 1,000 in the right units. And let's see, no, this is in SI units, so then you have to convert to this one. But that will come out to be approximately 10 Kelvin per kilometer. This is in SI.
But your model is valid only in the afternoon, not in the morning.
That's right. So I'm talking about average conditions. Actually, this is more like the average for the whole day.
Yeah.
But you're right. You can get sometimes, if it's clear, you can get an inversion where it's cold at the surface because the heat radiates out, and you can get an inversion. But on average, it does this. It cools with altitude, and this is for dry, but if you have moisture in the atmosphere, the moisture can condense and release heat. And so it's less than the dry situation, and it's like this. And this is common. So any condensable you have. So on Venus, you can calculate the dry lapse rate, which is this, and you'll get a number which is too big because it has those particles of sulfuric acid that condense, and they will lower the lapse rate. On Mars, it's pretty dry, but actually it's modified by dust. On Jupiter, you have ammonia that can condense. What we see are the ammonia clouds on the top of Jupiter. Okay, so now you go up to a certain altitude, and it gets cold at the top of the troposphere. Then it gets warmer again, and that's, on the Earth, is due to absorption of ultraviolet light by the ozone, okay, causing this structure. Eventually the ozone peters out, and you get cooling from carbon dioxide to space, and it gets really cold at the top of the mesosphere. And then it gets hot in the next layer. And in fact, if we have a big picture here, so this is temperature that's been missing off the bottom, temperature in Kelvin, and this is height, altitude, kilometers, so a very big picture here. Here's the lower atmosphere, and this is called the thermosphere up here, and you'll see the temperature there is about 1,000 Kelvin. So why is it so hot in the upper atmosphere? What's happening? Well, we have to think, what is temperature? Temperature is the motion, the speed of the particles. And so there's not much air up here, but they're moving fast. So when we measure the temperature by how fast they're moving, it's a high temperature, but there's hardly any air up here. We're just measuring the speed. And the problem is that up here, the molecules get destroyed into atoms. And molecules can absorb or they can radiate because the atoms move or can vibrate or they can rotate in the molecule, but when you just have single atoms, they can't get rid of their energy like that. So it's much more inefficient, and so this temperature becomes very hot. Now the other thing is the top of the thermosphere is called thermopause. It's called the exobase, the base of the exosphere. And from there, if atoms that are light, helium and hydrogen, they can escape from the Earth. And if it's a smaller body, other gases can escape. Let's put some other planets on here. Here's the Earth. This time I'm using pressure as a vertical coordinate, and this is temperature. And here's Venus, Jupiter, Saturn, Titan, Uranus, and Neptune. So this is temperature going up. This is altitude. This is high up here, low down here. But I plotted them with pressure because pressure actually is more fundamental. Altitude is Earth is a human thing. We think of altitude because it's easy for us, but this is more fundamental as pressure. And what you'll notice is that something funny is, there's something funny in common, which is that this turnaround point is for the Earth. This is the troposphere, this is the stratosphere. This turnaround point is about 0.1 bar, and it is for Jupiter, and it's close for Saturn, and it's similar for Titan, and Neptune, and Uranus. So, there's something in common there. So what is happening? Why do these atmospheres do this?
Sun radiation.
Sorry?
The sun is radiation.
Sun's radiation. It's related to that. Well, we know that these planets have stratospheres because there's something being absorbed. In the case of the Earth, it's ozone. In the case of Jupiter and Saturn and the ice giants, its particles are very important. There's hydrocarbons and also methane. They absorb in the visible and the ultraviolet. And also on Titan, there's methane and hydrocarbons absorbing as well. So those are the reasons why they have a stratosphere. But the common pressure is actually something else. What it means is that down here, the infrared radiation, so the infrared, which is coming heat from the Earth's surface, which is here, the heat, infrared, gets absorbed by the gas here in this part of the atmosphere. But when you get up to here, the atmosphere above you is thin, and the heat can go more easily out to space, and as a result, the visible and UV absorption of radiation begins to dominate. Okay? And that is a property which is independent to some extent. This pressure dependence is independent of the gas, the greenhouse gas. So basically, or to put it another way, what they've got in common is that we talk about infrared opaque, and that's the effect of greenhouse gases in the troposphere. And this absorption of infrared photons is related to pressure. So if you have a greenhouse gas molecule, and collisions of the molecule can take energy away, or they can add energy, and it broadens the absorption. It allows the molecule to absorb over a wider range of photon energies. Okay? And we call that pressure broadening. If otherwise, you just have very thin lines. So an absorption line would look like that. But instead, it looks like that. Because it's pressure broadened. Okay? And there's another thing that can happen. You have molecules like hydrogen, H2. And you might think, that doesn't look like a greenhouse gas. Because when we teach undergraduates about greenhouse gases, we say they have to have a dipole, a separation of electrical charge, which is easy for something like carbon dioxide, because you know that These are negative ends. That's a bit more positive, or with water. Whoops, it should be O. Those are dipoles, but this one, where's the dipole? It shouldn't interact with the radiation, but it does. It's the most important greenhouse gas on the giant planets, and it probably is important perhaps on some of these super-Earths that people talk about. Why is it a greenhouse gas? Because at pressure, collisions can distort the structure, the electronic structure, and they can make a temporary dipole. And so this is the greenhouse gas on giant planets, and on Titan, it's an important greenhouse gas. And people speculate that it could have been an important greenhouse gas on the early Earth, and also there's been a paper published suggesting for early Mars that there could be a way that early Mars was warmer. So these have the same kind of pressure dependence, and that actually is related to this common structure of these planets. Stratospheres, I said, are caused by visible and ultraviolet light being absorbed. And on the Earth, that's the ozone layer. We care about things like the ozone layer for astrobiology because ozone protects us from harmful ultraviolet less than 300 nanometers. If we had no ozone layer, you would be severely sunburned in tens of seconds. That would be a bad news. So this is important for advanced life. Well, okay, I shouldn't use the word advanced because some biologists say that we're not advanced, right? Bacteria are pretty advanced in some ways. But anyway, you know what I mean. Multicellular animal life, multicellular plant life on land, the ozone layer is important. And there's a lack of a UV shield. There's no ozone layer on Mars. So on Mars, you get ultraviolet light in the wavelength range from 200 to 300 nanometers. These photons hit the surface of Mars. You don't get photons much shorter than 200 because carbon dioxide absorbs this side. But on Earth, we don't get these. Even in Copacabana, we are safe from this wavelength range.
And how about Copacabana in Venus?
Copacabana and Venus. That's, well, there's other problems with Venus. I think UV is the least of your problems, but it's very little sunlight, only a small fraction gets down to the surface of Venus. And there is a lot of UV absorption in the atmosphere from the sulfur gases, as well as the hydrogen, as well as the sulfuric acid. There are also sulfur particles, elemental sulfur, things like S8. Okay, this absorbs in the UV. And there's also other things that absorb in the UV that we don't know what they are, but they're absorbing. And there's this thick cloud layer, and so, but this is not the problem. The problem is, on Venus, is the surface temperature.
Yeah,
And-
it's really hell, no?
Yeah. Yeah. Okay. So I mentioned that there was hardly any oxygen, less than 1 part per million before 2.4 billion years ago. But after this, the ozone layer was created. Oxygen rose at this time, and ever since 2.4 billion years ago, there's been an ozone layer. Okay. This is a definition of UV radiation. It's from 4 nanometers up to visible light, 400 nanometers. And these shorter wavelengths, like the ones that get to Mars, the surface, they damage organic molecules. It's one of the reasons why Mars is not a good place today at the very surface for biology. The other reasons, well, the other main reason is very dry and cold today. And the relationship between oxygen and the ozone column, so that's the total amount of ozone above you, that's the ozone column. The relationship is nonlinear. So here we have present atmospheric level of oxygen. So this is today. And this is a 10th of today, and a 100th of today, and a 1,000th of today. And here we have the ozone column density, number of ozone molecules per square centimeter. And today it's about 8 times 10 to the 18 on this graph. Column abundance is the integral of the number density over altitude, all altitudes from the surface up. And this determines the absorption, the column abundance. And you can see it's nonlinear. And even if you've got maybe 1% of present levels, it's okay, somewhat, because you have a pretty decent ozone layer. So it's very nonlinear. And that means that even though there was less oxygen, say 2 billion years ago, it was enough to shield the surface for simple life like algae or something like that. And this is roughly what the profile looks like in the stratosphere. This peak here is about 10 parts per million. There's a little puzzle here, which is that, remember, the temperature declined, and then it increased, and it continued to increase above this, up to about 50 kilometers. In the stratosphere, you go from a temperature that it keeps increasing, and yet the ozone peaks here, 25 kilometers. Why is that? Well, the reason is that even though ozone declines, up here there are more energetic ultraviolet rays higher up. And so it's the convolution of the amount of ozone and the energy of the photons that it causes the temperature to continue to rise up until 50 kilometers. Ozone comes from oxygen molecules. You break up oxygen, you make oxygen atoms. An oxygen atom and an oxygen molecule makes an ozone molecule. And then the ozone can absorb more ultraviolet light. And this was worked out in the 1930s by Sidney Chapman. And this is called the Chapman scheme. These 4 reactions is called the Chapman scheme. It's not quite right, because the theory doesn't quite match the observation, but this is the essential way that ozone is formed. So in other words, if you have an oxygen-rich atmosphere, you have an ozone layer. And that's important for exoplanets, because if there's photosynthesis on an exoplanet, it can make ozone, and the ozone can have a spectral signature that you can see in reflected starlight. So you say, oh, there's ozone. That means there's molecular oxygen. That means perhaps there's biology on another planet. These ones, O3 and just a single oxygen, we call it an odd oxygen. And this reaction, O3 plus O, goes back to our boring O2 molecule, and this stops the process. Okay. The Chapman theory, this is calculated from those 4 reactions, and this is observed. This is over Panama, 9 degrees north. This overestimates the ozone, and the reason is there are catalysts that we neglected. These catalysts are chlorine, bromine, hydroxyl radical, nitric oxide. These ones are natural. These ones are not so natural. These ones are from chlorofluorocarbons. And so this is also mainly from man-made chemicals. In chlorofluorocarbons, the chlorine is responsible for this, which makes the ozone hole over Antarctica. Okay? We were lucky. When they invented chlorofluorocarbons, they could have had bromine compounds, but they were more expensive. So they had chlorine compounds, which were cheaper. If they'd had bromine compounds, it's much more reactive, and we'd have an ozone hole over the entire planet. And the guy who invented CFCs, chlorofluorocarbons, he also invented lead tetraethyl, which was the lead that goes in gasoline. Never mind.
He made a lot of money, right?
He made a lot of money, but he ended up killing himself, actually. He had many patents, and he got a disease when he was old, but he invented a system of pulleys to get him out of bed, and he strangled himself with his invention. Okay, you see the ozone layer often in the evening. You may not know that, but you do. Because ozone also absorbs not just in the ultraviolet, but in the visible. It absorbs in the yellow. Now, normally, it's not much. So when you look overhead, you don't notice this tiny, tiny absorption of the yellow by ozone. Okay? But when the sun is low in the sky, it mostly looks like this at twilight or dusk. It's blue. But if there were no ozone, the yellow wouldn't be absorbed. We'd have yellow skies every day. So you see the ozone layer every day because you see a blue dusk, you see a blue twilight. This is absorption over the so-called Chapuis bands in the visible, peaking at 600. That's yellow. Our blue sky is caused by Rayleigh scattering during the day, which is this wavelength-dependent scattering, favors the blue, scattering all directions. But at twilight, when the sun is very low in the sky, this is the sun, or where the sun is, then ozone actually is very important for the blue.
Is that on the right,
Yeah.
a synthetic image or something in the ozone hole?
This is calculation.
Is the ozone hole not?
The ozone hole's not completely clear of ozone.
Okay.
Yeah. Okay. Now I'm going to talk about some climate issues. What makes the Earth... Well, before I do that, are there any questions so far on anything I've said? Because I'm covering a lot of ground. Yes?
Do you think that there was a UV shield in Mars in the past? Like
Oh. Well, only very speculatively. So an ozone layer requires oxygen. Okay. If there was an ozone shield in the past, you have to get oxygen. Where does oxygen come from? Life, biology. So I think the only possibility for Mars having an ozone shield in the past is if there was photosynthesis and a lot of oxygen pumped into the atmosphere. But otherwise, I think, I don't think so.
So, just with curiosity, a follow-up question. So is it possible to estimate the time that the ozone layer will disappear if you cut the supply of oxygen?
Is it possible to make it
the time scale that destroy the ozone layer if you just cut the supply of oxygen?
Oh, well, it's very hard to get rid of the oxygen because the oxygen is so abundant. It's 21% of the Earth's atmosphere. And if you could play God and you say, let's have no more photosynthesis now, okay, let's wait. We'd have to wait about 10 million years, maybe longer actually. You'd have to wait maybe 25 million years to get rid of the ozone layer, just from the oxygen decline. It would be very slow, okay, because there's a lot. So ever since 2.4 billion years ago, there may have been fluctuations in oxygen, but you don't need much oxygen for a good ozone layer. Just a little bit, about 1% of present levels. So 1% of 21%, which is 0.2%. Yeah, 21% divided by 100 is okay. If you drop below that, then the ozone layer goes. Okay. But it's been above that level, we think, based on geological evidence. It's been like above that level for 2.4 billion years on the Earth. Yeah. Yes?
Is it possible to think of temperature inversion when the atmosphere is not so dense?
Yes, you can get a temperature inversion. There may be one possibly on Pluto, because it has some methane in its atmosphere. So on Pluto and on Triton, Jack mentioned that Pluto, some people think of it as a Kuiper Belt object, right? And also Triton, the largest moon of Neptune, also has the same properties as a Kuiper Belt object. It has nitrogen ice on its surface and methane ice. But some of it is vapor, and the methane can photolize and make haze particles, and that may absorb enough sunlight to get a bit of an inversion.
So that point of that limit of 0.1 bar.
Yeah,
it also has a chemical dependence.
Yeah, that only really applies for thick atmospheres. So if you have a thick atmosphere that is at least 1 bar surface pressure, or has no surface but just as a giant planet, then that will apply. But there could be exceptions with these thin atmospheres, okay, with an inversion. Yeah. Let's talk about climate, because climate is the most important thing for habitability, okay? And the reason I introduced structure is because structure is important for climate, it turns out. And I have to introduce some terminology, 3 things. And the first one is atmospheric scientists and also astronomers. So this should be okay for astronomers. They use these terms: optically thick and optically thin. Now you notice that you can't see this very well, but this is a bit like 10-pin bowling, or in British English it's called skittles, where you bowl. And if you have a lot of these pins, your ball will hit. And if you just have a few, it won't. So when you have a photon going through air, which has a lot of greenhouse gas, if it's an infrared photon, it will mostly be absorbed. We call that optically thick. It just means opaque. And if it doesn't get absorbed, we call it optically thin, which means transparent. Okay? It means a poor chance of absorption. And this is the equation. This is the incident intensity of radiation, and this is what you get after a certain distance, which we put in terms of something called an optical depth, with the Greek letter tau. If that optical depth is bigger than unity, then we call it optically thick. If it's smaller than unity, we call it optically thin, poor chance of absorption. Okay. And in fact, we can go back to our structure here, and this is an average for Earth, giants, and Titan. Here's the troposphere dominated by convection down here. This is this optical depth parameter. It's big, so it means infrared photons will be absorbed here. Then up here, you get a transition from convection to radiation. And up here it's very thin. This number is low, and this means that the inversion begins to dominate. And these are average numbers for all of these bodies, all of these atmospheres. This is set, of course, by energy, the star flux, There may be some internal heat. There may be infrared coming up from a surface, and it sets up this profile. We care for astrobiology because a habitable planet has liquid water on its surface. And also in astronomy, we talk about a habitable zone around a star where liquid water is stable. But this all depends upon the atmosphere. So the way I'm going to give you some insight into climate is to do some thought experiments. So let's start with a very simple case of a planet with no atmosphere. Then we add a thin atmosphere and then a thicker atmosphere and see what happens. But I have to introduce some other terms. 3 more terms. One is the Stefan Boltzmann law. One is something called the effective temperature of a planet. And one is something called the skin temperature of an atmosphere. So you know if you see something really hot, it's white hot or red hot. The peak of the intensity of emission depends on temperature. This 6,000 Kelvin is like the sun. It peaks in the visible. But for a cooler star, say which has a surface temperature, surface on a star is just where we can see photons, 3,000 Kelvin. It would be in the near infrared, the peak of the emission. And what we talk about, Jack mentioned the term black body. I'm going to define it. A black body is something that has an idealized spectrum depending only on temperature. That's the way I think about it. And what it means is that there's an equation called the Planck function, and if you plug in the temperature, it defines this curve. Just one parameter, the temperature. And any of these bodies will have a flux that depends on the temperature to the power of 4 in watts per square meter. This is the Stefan Boltzmann law. That's all it is. Gives you the flux out. So if we plot the solar flux, this is the sun as a black body. It peaks in the visible. And here's the flux, infrared, coming from the surface of the Earth and the atmosphere. It peaks out here in the infrared. This one peaks in the visible. And these are units of watts per meter squared per micron wavelength. And the effective temperature of the sun was about 6,000 Kelvin. And for the Earth, it's 255 Kelvin. Okay? And it's easy to understand why it's 255 Kelvin. Because if we have the Earth in space, I can draw the Earth. Here it is. And here's the sunlight coming in. And at 1 AU distance, this is 1,360 watts per square meter. That's the solar constant. But half the Earth is in darkness, so we have to divide by 2 to get an average. And also, some sunbeams are glancing angles, right? They're not hitting normal to the surface. They're hitting at a glancing angle. So the daylight, nighttime means you divide by 2. And the glancing angles, it turns out, if you do an integral, it's also divide by 2. And then we have this flux. So we want an average flux. And that's going to be 1360. Then this reflects some sunlight, which we call the albedo. So it's 1 minus the albedo. And this is the average flux absorbed by the Earth. If you do this calculation, the albedo is 0.3. 30% gets reflected. This number here, if you do this calculation, is approximately 240 watts per square meter. That's absorbed. Then the Stefan Boltzmann law says the Earth will radiate in the infrared according to some temperature, the effective temperature. And if you solve this equation, this is just a constant of nature, then it turns out the effective temperature is 255 Kelvin. Half, factor of half, daylight, nighttime, other factor of half, glancing sunbeams. So that's the effective temperature. So I said I had to define three things: Stefan-Boltzmann law, effective temperature, skin temperature. What's the skin temperature? Okay, this one's a little more complicated. But bear with me, this is the most equations I have on any slide. So start at the bottom. At some level in the atmosphere, photons, it goes from optically thick, opaque, to the infrared, to optically thin, relatively transparent. This level we call the emission level. And on the Earth, it's about 5 kilometers altitude, idealized. We have the Stefan-Boltzmann law, the effective temperature, the infrared photons go up. Imagine a slab of atmosphere. It absorbs a little bit. So this factor here gets absorbed. But it also radiates up and down by the Stefan-Boltzmann law at whatever temperature it reaches, called the skin temperature. So we say what goes out must equal what comes in, energy balance, out, in, solve, the temperature skin. And it turns out to be a very simple mathematical relationship to the effective temperature. If this is 255 Kelvin for the Earth, the skin temperature is 214. And this is actually quite similar to the Earth's tropopause temperature, where it becomes relatively transparent to the infrared photons coming up from the Earth. And it's a pretty good, if you did this for the other planets, you would also get a pretty good estimate. You could do it for Titan, whatever, Jupiter. You'd get a pretty good estimate of that turnaround temperature that we call the tropopause, the top of the troposphere. Is that okay? Okay. So 3 things, and now we can apply it to planetary climate. So the first planet I want to consider is one with no atmosphere. What would the temperature be? It would be like this. The Earth, an Earth-like planet at 1 AU, it would have, assuming it's spinning rapidly and a relatively uniform temperature, it would be 255 Kelvin. Okay? Simple. Okay? That's the first example. Now supposing we add a thin atmosphere that's optically thin to the infrared. Now what's going to happen? What's the temperature going to be at the top of the atmosphere? It's going to be our skin temperature. It's like that idealized thing okay, so we can now think of a diagram, and we're not going to allow convection. Here's our surface temperature, the effective temperature. It's radiating like a black body. Optically thin atmosphere at T skin. And because we're not allowing convection, there's a discontinuity here. It's not physical. Okay? What will really happen is that convection will set in. Okay? So let's allow it to convect. Oops. Let's allow it to convect. So now this is optically thin, but convecting. So it actually looks more like a real atmosphere now. Convection is setting this lapse rate, like we discussed earlier. But the surface temperature is pretty close still to the effective temperature. For the Earth, that's 255 Kelvin. Because there's no greenhouse gas here. This is relatively transparent to the infrared by our thought experiment. Now let's try and make it a real atmosphere. So we're going to be like a recipe in the kitchen. We put some greenhouse gas, stir it in, okay? Now what's going to happen? So now we're making it optically thick at the bottom. That means it's going to absorb some of this, absorb this infrared photons. And the emission level is no longer the surface, but wherever it becomes optically thin. So it shifts up like this. Now we've moved to a different surface temperature, higher than the effective temperature. And this difference is the greenhouse effect. By adding in greenhouse gases into a convecting atmosphere that's optically thick, we have produced a greenhouse effect. And if we stir in more greenhouse gas, we can make this into a Venus. It will just shift along here, making a bigger greenhouse, although at the top here, because it will still be the skin temperature. Okay, basically that's how the climate system works in simplicity. We have a greenhouse gas, and this level here, the optical depth from the top of the atmosphere is about unity, and below it's bigger. So here this is opaque to the infrared, this is relatively transparent. And in fact, understanding climate of any planet just adds more realism to this picture. This is 1D. This is assuming average over all wavelengths. We could do wavelength dependent, pressure dependent, temperature dependent infrared absorption. We could add scattering. We could add clouds. We could do 3D instead of 1D. We could do dynamics on the 3D world. We could do oceans. We could add ice. We could put in the biosphere. But in essence, it's just more and more complexity to this basic picture, average picture. And so let's see, I'm going to get towards the end here. If you look at the, if you look down from space, and this is wavelength in micrometers, and this is the spectrum you see from the Earth. And these curves are black body spectra at different temperatures. And this is actually looking at Africa, so it's hot. This is North Africa. The surface temperature when these measurements was taken was 320 Kelvin. You can see the surface here on this line, 320 Kelvin. But elsewhere, the atmosphere is absorbing, such as here. And you can only see the photons coming from about the level where the atmosphere is 220 Kelvin here, or about 280 Kelvin here. So at the 15 micron absorption of CO2, you're seeing photons from up near the tropopause. Only here, in a so-called window of 11 microns, can you see the surface. If we look at exoplanets, and we want to determine the surface temperature to see whether it's habitable, we need a window. If we don't have a window, imagine it has a different atmosphere and we see something else down here, we just see the atmosphere. We can't see the bottom of the atmosphere. So it's difficult because there are planets that you can't see through. So for example, Venus. If you look in most of the infrared spectrum, you cannot see the surface because it's so absorbing. And so how do you know the surface temperature? You don't in the infrared. You have to go to the near infrared, or you use some other wavelength. And I will say more about looking for life on other planets using these kind of spectra, because look, we can see ozone. We detect this feature at 9.6, 9.7 microns. We know there's ozone there. There's an absorption line. That means there's oxygen. That means there could be life, photosynthesis, producing oxygen. And actually, down here, it looks a bit noisy, but there's also methane absorption, another biogenic gas. So you can, from these kind of spectra, you could determine, in principle, if there's a window, the surface temperature, that tells you whether liquid water is possible. You could determine biogenic gases. And you could determine whether the planet is alive. But I'll say more about that later on. And now I'm just going to summarize what I said in this lecture. So when we look at solar system bodies, we can understand something about the variety of atmospheres. We can understand the classification, reducing, hydrogen rich. They have organic hazes, oxidizing, hydrogen poor. Sulfate hazes, very thin on the Earth, global on Venus, absent on Mars today, but perhaps it would have had one in the past. I talked about how the structure has some similarities on different planets. I talked about stratospheres and ozone. And I discussed some basic issues of climate physics. If you add greenhouse gases, it changes the structure, produces a greenhouse effect. And these principles are all essential to understanding the nature of a climate, the nature of an atmosphere, and whether a planet might be inhabited. But I will mainly talk about that in the fourth lecture, by way of telling you the story of how atmospheres originated and how they evolved. Any questions?